let's talk about differential equations, specifically how to solve them exactly. And the general idea is that if I give you some sort of differential equation, I'll do the one from the notes to match note set 25. The goal always for differential equation, the goal to find the solution, which means finding an expression for the dependent variable. What's that mean? The dependent variable is the one that depends on something. So y depends on x. Y is the function of x. So we need to find what that means. And what's special about whatever that equation is, for example, let me see what the actual answer is for this differential equation. The answer for this, which we'll solve for, the answer is y is equal to 6e to the negative 2/3 x minus e to the negative x. That x is in the numerator with the 2. Let me make that clearer. Minus e to the minus x. If I were to graph this, let's say I were to graph this. And again, I don't know what this graph looks like perfectly, but some sort of negative exponential. It's some sort of negative exponential. So maybe it looks something kind of like this. The idea is that if I were to pick any arbitrary point, let's say I pick this point, this is some x comma y. Maybe I say that this is, I don't know what one it actually works for this equation. Let me just call this x1, y1 to make it specific. The idea is that that point satisfies this equation. So if I look at this y value and I were to take the derivative of it, dy dx, let me write it over there, dy dx, if we look at this first term, we take down the exponent, which is negative 2/3, and multiply that by 6. So that's going to be negative 12 over 3, which is negative 4 e to the negative 2/3 x. And we take the derivative of this guy, which brings down a negative sign. So that will be plus e to the minus x. So if we plug this specific point in to this, and then into those values, that equation is true. We basically have a relationship between the function itself and its derivative. And these other things that are there allow the equation to be true. That's what it is from a mathematical perspective. Now, from a physical perspective, let's say, the example that I'll give, actually we'll leave that. The example that I'll give that you'll hear about in the future more is a vibration example, which this system actually isn't, that doesn't describe a vibrating system, this first order TPQ, a vibrating system second order. But the general idea, if I were to give you some sort of second order differential equation, I'll just make it with just a spring, it's easier. Is that I will have some position of x. X will oscillate back and forth possibly, where that motion depends on the force. So the motion depends on the forcing function. right? That makes sense. If I'm pulling on it, obviously it's going to move a certain way. And that movement depends on the direction of the force and the magnitude of the force. How large is it? Now, another thing that determines the direction or the position of the mass is where it started. So let's say I have a mass that started all the way out here. This is our equilibrium point, what we would call, x naught at t naught equals 0. And maybe I let go, we have motion. So this initial condition causes motion, right? Because I've supplied some energy to the system. I've pulled the spring. I've given it potential energy. I let go. It's going to start moving back and forth. There's no forces on this in the one I just drew. Just the fact that I stretched it a small amount. Now it'll move back and forth. So these two things are related respectively to the particular solution. Basically, how does the mass move because of this force? And the homogeneous, how does it move because of initial conditions? So if you ever have something that is on the right, you can solve for it in that case, and that will give you the motion due to the force. If you have nothing on the right, meaning it's 0, then you have the solution x based solely on the initial condition, and the sum of them determines the entire motion. For example, I might have some graph that just due to the initial condition, maybe it looks something like this. It's oscillating back and forth. The mass, this is time and this is x. But due to the force, maybe the force is starting negative and it's bigger. Maybe it's something like this. And maybe it's possibly at a different frequency than it would actually move at compared to when you let it go. Maybe it's a motor that's spinning a certain way. This would be like our homogeneous solution. This would be our particular solution due to the force. And the sum of them, if you add them together, that gives you your total solution. Maybe that looks something like, it's really difficult to draw because you have two different frequencies acting. But you'd have some sort of weird thing that's possibly happening because of those two functions being added together. And that's what we're doing with differential equations. We're trying to find the physical response of something due to its initial conditions and due to some external force that is causing something to happen, whether that's motion of a mass or temperature changes in a heated part or fluid motion or whatever. Our general idea is that we will always first find the homogeneous solution. We'll then find the particular solution if needed, meaning that we have a forcing function. If I gave you a problem with nothing on the right, it was just 0, then you wouldn't have a particular solution. All the motion is just based off the initial condition. There's no force acting. You're not going to change the motion outside of just the homogeneous part. Add together. And then find any constants from initial conditions. So let's go ahead and do that for this example from the notes, where I give you 3 dy dx plus 2y is equal to e to the negative x, and I give you an initial position or initial condition. It's not necessarily position here. This is dy dx, not dx dt, of y of 0 is equal to 5. So first what we'll do is we will look at the homogeneous. We'll say that 3 dy dx plus 2y is equal to 0. And we're trying to find some solution for y that satisfies that equation. And the common thing that I like to do is just to assume a solution, because that will typically work most of the time. The thing that doesn't work all the time that might get complicated is separation of variables, which for first order differential equations you could do, where basically if you were to do that, you would move this to the other side, move everything around, and end up having the y's on one side and the x's on the other, integrate both sides, you get an answer. But what you can do instead is assume that your homogeneous solution is something like ce to the lambda, in this case x, because that's the variable that we're dealing with, is x. So we know we need the derivative of that y value, so we'll go ahead and take its derivative. We can say that dy dx, that'll take down a lambda, give us c lambda e to the lambda x. This would be 3 c lambda e to the lambda x plus 2 c e to the lambda x is equal to 0, right? This is dy dx, this is y. We can divide by the constant, because the constant won't be equal to 0. That would mean there's no motion, and that's kind of useless. It's a trivial solution. So we can cancel the c's, and we can cancel the exponentials, because those are never equal to 0. That will just give us 3 lambda plus 2 is equal to 0. That tells us that lambda is equal to negative 2 over 3. So what that means is that your homogeneous equation is c e to the negative 2/3 x. Note, we do not know the c yet. That c is determined from initial conditions. So we have to plug that into our final solution at the end, because that dictates the entire initial condition of the object, or whatever the phenomena is. So this is good. We'll save that. Now the particular equation is the same exact ODE, except now we include the forcing function on the right. And the forcing function of this problem was e to the minus x. And what we assume depends on the forcing function. Because whatever I have on the left after taking derivatives and stuff, it has to equal e to the minus x. So we are going to assume that our particular solution is of the form e to the minus x, but we don't know the constant associated with it. But it has to have the same exact exponent, because of the fact it needs to match the right side at the end of the day. So what we'll do is we'll take the derivative of that with respect to x. That'll give us a negative a e to the negative x. We'll plug that in, so you get 3 minus a e to the minus x plus 2 times a e to the minus x is equal to e to the minus x. And what we can see is that all of these e to the minus x's will cancel out, because we can divide by them. That'll give us negative 3a plus 2a is equal to what? 1. Good job. So it's equal to 1. So if we add those together, we get negative 3a plus 2a. That's negative a. It's equal to 1. That means that a is equal to negative 1. So this is going to be, if we come back to this, yp is a, which is negative a times e to the minus x. That gives us our particular solution. Note, this won't depend on initial conditions. There's no c's here, because this is only due to the force. This is only due to the external thing. It has nothing to do with the initial conditions of the system. This is just strictly some external thing that's moving. It doesn't care about what was happening before the mass started moving or the heat started transferring or whatever. This is just strictly the thing due to an external motor or an external heat source or whatever. So our total solution now is the sum of those two. I'll write it in the order we found them. YH plus YP. If we scroll back up, see that YH is C e to the negative 2/3 x minus e to the minus x. That is our Y total. And based on our initial condition, which I'm rewriting now, that Y of 0 is equal to 5, we can plug in, but this is saying when x is equal to 0, so we'll plug in Y of 0 is equal to C e to the 0 minus e to the 0. That whole thing has to be equal to 5. So you have C minus 1 is equal to 5. You end up with C is equal to 6. So that means that our total solution is 6 e to the minus 2/3 x minus e to the minus x. So this is basically the response of the system due to both its initial condition and the forcing function that's on the right. Okay. So in that case, if you compare the particular, let's just write those down again. The homogeneous was C e to the negative 2/3 x, and the particular was negative e to the minus x. If you look, these are linearly independent, meaning I cannot multiply, let's say, YH by a constant and get YP. Like I can't just say, oh, let's multiply this by 3 and expect to get the same exact answer. Because they have different exponents in the exponential. If they had the same exponent, then we have a problem. But they don't in this case, so we're okay. Let's do an example where I have the same exponent. We'll see what that looks like. So let's say I give you a different differential equation. That's where I can find it. 2 dy dx plus 3y is equal to e to the negative 1.5x. So very similar. But the big thing here is if you compare this to the other one, the only thing I changed was this exponent. You might be thinking ahead, oh, that looks kind of similar to our homogeneous. That was done by design to demonstrate this. So again, what we'll do is first we'll do the homogeneous. Well, let's have 2 dy dx plus 3y is equal to 0. So we will assume that our y homogeneous is something like C e to the lambda x. And this matches the other problem, but we'll do it again just to be thorough. We'll take the derivative with respect to x. You get C lambda e to the lambda x. So you get 2 C lambda e to the lambda x. That's dy dx plus 3y. The whole thing is equal to 0. And just like before, the e's will cancel and the c's will cancel. We get that 2 lambda plus 3 is equal to 0. You get lambda. Oh, sorry, it's not the same exact problem. It's a little bit different. The numbers are a little bit different. This gives us 3/2 negative, which is negative 1.5. So that means that our homogeneous solution is C e to the negative 1.5x. Now, keep this in the back of your brain. If you do the particular solution, that was equal to e to the negative 1.5x. We will make an assumption right away. And the first assumption should be that we'll match the forcing function. So this would be a e to the negative 1.5x. And that's where you should have some pause. Because if you compare these two, if I multiply y sub p by something and it gives me y sub h or vice versa, that means that they are dependent on each other from a linear perspective. So for example, if I multiply yp by c over a times c over a, that'll be a e to the negative 1.5x times c over a. Oh, look, you got the homogeneous. Remember, C and A are just numbers. So C divided by A is some number. Maybe it's 8 over 2 or something. I'm multiplying by some constant, and that's giving me back the homogeneous. We cannot have that. That's not allowed. So instead, what we do to fix that problem, what we do is we add, or when I say add, we include another x next to it. I'll do that in black so that it's clear. We have another x. Now we can't multiply one equation by a number to get the other because this top equation doesn't have an x. There's no x here. And because of that, now they're linearly independent. So now what we'll do is we'll take the derivative of this with respect to x. You have to note we have an exponential times another function. We have to do the product rule. So this would be a. We can do the first times the derivative of the second. The derivative of the second being x is 1. Plus the second times the derivative of the first. Like that. Oops. That's a bit cleaner. Right? Because that would be the derivative of the exponential, and negative 1.5 comes down. So if we wanted to rewrite that a bit, this would be a e to the negative 1.5x minus 1.5x e to the negative 1.5x. And that's our first derivative of our particular solution. We'll go ahead and substitute that in now. So you get 2a e to the negative 1.5x minus 1.5x e to the negative 1.5x plus 3 times y. What is y? Well, that is what we assume to be our initial, our original particular solution. It's going to be ax e to the negative 1.5x. That whole thing's going to be equal to negative e to the negative 1.5x. So let's distribute that 2a. Negative 1.5 times 2 is negative 3. And now we can see something really nice that happens, that this guy and this guy are identical. They're equal and opposite. So they will sum to 0. So end up having 2a e to the negative 1.5x. That's equal to e to the negative 1.5x. The exponentials can cancel. That gives us 2a is equal to 1. We get that a is equal to half. Is right. Okay, cool. So that would mean that our particular equation, which originally ax, would be 0.5x e to the negative 1.5x. That is our particular solution. We come back up, we see that that's what we had in red at the top. We're putting in the a now, which is a half. Okay. Our total solution is the sum, so y total. Our homogeneous, if we scroll back up, was c e to the negative 1.5x. c e to the negative 1.5x plus 0.5x e to the negative 1.5x. And now we need to find c. We'll go ahead and use our initial condition. We come back up, we see that we have y of 0 is equal to 5 again. Double check that that's actually true and I didn't make it up. Yeah, that's what it is. Y of 0 is equal to 5. So if we do y of 0, that'd be c e to the 0 plus 0.5 times 0 e to the 0. Basically, everywhere that there's an x, you're plugging in 0. This will be c plus 0. This whole thing has to be equal to the initial condition of 5. So we get that c is equal to 5. So our total solution is 5 e to the negative 1.5x plus 0.5x e to the negative 1.5. And that's a brief reminder of how to do the first order differential equation solving, where we have some solution that we're assuming. We do both homogeneous and particular. And the big thing is we have to make sure that the particular and the homogeneous are not linearly dependent on one another. Otherwise, you end up with weird results that aren't physically accurate. So to fix that, you include an extra value of the independent variable, like x in this problem, for example, and then you continue the problem as is. Okay, if you have any questions, please let me know. Thanks.